Okay, let's dive right into this explainer. If you look around wherever you are right now, whether it's the screen you're watching this on, a desk, or just a random piece of paper, you are surrounded by flat surfaces, things mathematicians call planes. Today, we're focusing on this specific chapter to explain exactly what happens when straight lines interact on these surfaces. Sounds simple, right? Well, as we're going to see, the rules governing these lines actually create a beautifully structured, almost magical logical system.
So here's the ultimate puzzle we're going to solve today. How can knowing just one single angle reveal the exact measurements of 7 others? Think about that for a second. Imagine I give you this complex geometric traffic jam of intersecting lines, and I only give you one number, just one. By the end of this explainer, you'll have the exact mathematical toolbelt needed to confidently map out all the hidden angles without ever picking up a protractor.
To get there, here's our roadmap for the chapter. 1. When lines collide. 2. The protractor problem. 3. The power of parallel lines. 4. Crossing with transversals. And 5. Solving the angle puzzle. Let's get to it.
Starting off with Section 1, When Lines Collide, the basics.
Let's look at what happens when straight lines literally crash into each other. When line L and line M cross at a single point, boom, they immediately form exactly 4 distinct angles. You've got A, B, C, and D. You literally cannot cross 2 straight lines without creating this exact 4-angle scenario. It's an absolute fundamental law of flat geometry.
And this brings us to the first 2 tools for our tool belt. First up, linear pairs, which always add to 180 degrees. See, a linear pair is just adjacent angles sitting right next to each other on the exact same straight line. Since a straight line is literally a 180-degree turn, those 2 side-by-side angles have to perfectly share that 180 degrees. Second tool, vertically opposite angles. Look at the angles directly across from each other at the intersection. The rule here is that they are identical twins. If one is 40 degrees, the one directly across the street is also exactly 40 degrees. No exceptions. Moving on to Section 2. The protractor problem. Math versus reality.
Now, before we get too far, we've got to address a kind of fascinating glitch in the matrix. Why don't real-world pencil measurements always match our perfect math? Well, human error and pencil thickness get in the way. In pure theoretical math, a line has absolutely 0 thickness. It's totally abstract. But in reality, your pencil lead, your pen ink, even the pixels on your screen, they all have width. Add that to a slightly misaligned plastic protractor, and things get messy. This is exactly why using geometric logic, the rules in our tool belt, is actually way more reliable than measuring things by hand.
Okay, Section 3. The power of parallel lines. Never touching.
If intersecting lines are all about collision, parallel lines are about perfect avoidance. They run side by side, and no matter how far you extend them, literally out to infinity, they will never ever touch. A great way to visualize this is by just grabbing a square sheet of paper. Fold it in half, open it up, and then fold the edges into that center crease. By doing that, you're forcing the paper to create lines with identical geometry. Because the edges were straight and your folds are symmetric, those vertical creases are now perfectly parallel. It's such a cool physical proof you can hold right in your hands.
All right, Section 4. Crossing with transversals. The master key.
Sometimes it's kind of tricky to know for sure if lines are perfectly parallel just by eyeballing them. So we need a master key. Enter the transversal. I'll slow down for a second because this is literally the most crucial vocabulary word in the whole chapter. A transversal is simply a line that intersects 2 or more different lines. It acts like a geometric bridge, connecting the math of the top line to the bottom line. It unlocks everything. Check this out. Notice how a single transversal, line T here, slicing through lines L and M instantly generates 8 unique angles. We suddenly get a top intersection with 4 angles and a bottom intersection with 4 angles. That's 8 distinct pockets of space, and because they were all sliced by the exact same line, they're secretly mathematically related.
Which brings us to corresponding and alternate angles. If we were to slide tracing paper over this, we'd see these sets perfectly aligned. Think of corresponding angles as sitting in the exact same chair, just at different tables. The top right angle at the top intersection matches the top right angle at the bottom intersection. Alternate angles, on the other hand, are on opposite sides of the transversal, diagonally matching. And here is the magic rule. If those 2 horizontal lines are perfectly parallel, these matching angle sets are always identical.
Bringing us to Section 5, Solving the Angle Puzzle. Unlocking all 8.
It's time to test out our new tool belt. Here is our full intersection matrix.
And our only clue, our only piece of intel, is a single angle down in the bottom right corner measuring 135 degrees. We've got parallel lines L and M sliced by transversal T. Out of 8 angles, we only know angle 6.
135 degrees. That's our anchor. And believe it or not, that's literally all we need to crack the whole system. Let's watch the dominoes fall.
Step 1. Corresponding angles. Because lines L and M are parallel, angle 6's corresponding partner up top, angle 2, is also 135 degrees. Step 2. Vertically opposite angles. Angle 8 is across from 6, so it's 135. Angle 4 is across from 2, so it's 135. Boom! Half the board is filled. Step 3. The linear pair. Angle 5 sits right next to angle 6 on a straight line, meaning they must add to 180. So, 180 minus 135 gives us 45 degrees for angle 5.
And just like that, the puzzle is solved. Because we found angle 5 is 45 degrees, its vertically opposite partner, angle 7, is 45. Angle 5 corresponds to angle 1 up top, making it 45, and angle 1 is opposite angle 3, making it 45. The entire matrix is perfectly solved from a single number. It really shows just how powerful and infinitely reliable geometric logic actually is.
Now that we've totally mastered flat planes together, I'm going to leave you with a final mind-bending thought. Everything we just explained in this chapter relied on a perfectly flat surface. But what if you tried to draw these parallel lines and transversals on a curved surface, like the Earth or a sphere? Do the angles still add up the exact same way? Do parallel lines eventually meet? I'll let you ponder that, because math is always pushing boundaries. Thanks for checking out this explainer with me, and keep exploring.